Hello, good morning. Welcome to the class ECE451. Today we will study the rule Locus. Rule Locus means the orbit of roots, the orbit of poles, of the poles. The case is when the system has some parameters. When the parameters change, the location of poles will also change, right? The poles will change. Then we have an orbit of the poles. We call that orbit of poles rule Locus. ECE451. This is which week? Fifth week, Monday's class. We consider rule Locus. That is the orbit of poles of a system when parameters change. Okay. So firstly, for simplify, we want the system have a uniform form, right? So the first thing, write the transfer function in form. It is a T of S, G of S. T of S transfer function of the whole system equal to 1 plus K G of S. Numerator doesn't matter because we are checking the poles, right? Checking the poles. So here, for convenience, we can just think it is S, right? Or anything, yeah, or any like you want to say like a numerator of S, right? Any in of S, okay? So we put this for convenience. Why we use this way? This way can be realized as a unit feedback system. Not unit feedback, it's a feedback system. K is here, plus, minus. Input is here, output is here, right? So this transfer function you can realize like this way. If the transfer function is different, you can rewrite it. For example, like T of S equal to S cubed plus 3 plus K S squared plus 4S plus 5 plus K. Here's a S cubed plus 1. For example, we have a system looks like this. Then we can rewrite it as S cubed plus 3S squared plus 4S plus 5, all the terms without K, and K of K times S squared plus 1. So now K, we put K together. Then I divide by this term, this one without K, right? I divided by it. So this is 1, and plus here's a K S squared plus 1 over S cubed plus 3S squared plus 4S plus 5. Here's S cubed plus 1 over S cubed plus 3S squared plus 4S plus 5. And we use this as G. This is G of S. This one, they're different, so this is some N of S. Then the rule Locus of T of S equal to root locus of G over 1 plus Kg. Right? G is this one. G is this one. So we can study the root locus of these. That is a totally same with the root locus of T of S. Yeah, because they have the same denominator. They have same denominator. The poles related with the denominator equal to 0. Right? Denominator equal to 0. This one. Okay. So we can use this as a, like a assumption. We always study the root locus in this way. If it is not in this way, you try to do some change. Similar like this. You can have this one. Yeah. Okay. Then okay. Secondly, we have a tool. We have a computer tool, MATLAB. MATLAB, we have a command root locus, CUS, LOCUS, root locus. We have this function. You just run this function, you can see, like here's a G. Here's a G. Give us the root locus of G over 1 plus Kg. Yeah. And we can have a look. Suppose G is transfer function. I give like 1 over S squared plus 1. Okay, S squared plus 1. So this is a I give this is first order. Give a 1 and a 1. 1 and 1. 1 and 1 in the numerator, and that means S plus 1 in the numerator, and S squared plus 1 in the denominator. Right? This is G, and then root locus of G okay, so this is the root locus. We have some curves, right? Here we have two curves, one in the circle, one in the straight line, and actually they are connected as the blue part and the green part. They related with two poles. You see, this is a G, right? This is G, and the T will be G over 1 plus Kg. I don't have K, so I put G. This is the transfer function when K is 1, right? This is K is 1. Oh, it's false R. Well, MATLAB cannot cancel the numerator and denominator, the same factor. They cannot cancel. Cannot do simplify. Actually, this T should be a second order system. The second order system. Second order system has two poles, and each pole gave us an orbit. So there are two orbit. So this is the root locus. Root locus looks like this. All right. Okay. All right. With these two, we can do some works on it. I'll say the properties. Okay, properties of the root locus of 1 plus Kg of S. I write this way. Yeah, root locus, right? The root of this part. The root of this part. Root of this. So we can also say the root locus of this one. The orbit of roots of this one. the first one, yeah, we suppose k run from 0 to positive infinity, and we do some restriction here. Actually, you can use any k, right? But here I start consider k is positive side. Then k0, what happened? K0, what happened? K0, now the transfer function equal to g over 1 plus kg. It is just g, right? K0. So in this case, t's poles equal to g's poles. Poles of g and poles of t, they are totally same. Now we look at this example. This example, we have a g is s plus 1 and s squared plus 1, right? This is a g. This is a g. This g has poles positive and negative I, right? Positive and negative I. You see here, the cross here, and the cross here. This is a 1, right? This is 1 of I, yeah. And the 0 of the 0 part is 0. So 0 plus I, and this is a 0 minus I, right? Positive and negative I. So this cross, actually in the graph of the MATLAB, these two cross according to the poles of G. So we use cross. You know the PZ map, we use cross for poles and use circle for zeros. So here the cross, actually they are the poles of G of S. It is also poles of T of S when K is 0. Okay, so this is K0 case. Let me move here. Alright. And secondly, we consider k go to infinity. Actually, negative infinity is the same thing. In this case, t of s equal to g over 1 plus kg. So what is this one? Okay, we write it again in this way. 1 over k plus g. Here's g over k. So denominator, this is denominator. Poles of T of S according to the root of 1 over k plus g, right? That means 1 over k plus g equal to 0. But k go to infinite. So 1 over k go to 0, and g of s equal to 0. So this part according to g of s equal to 0. What is this? What are these? According to zeros of g of s. You see, we have example here. This 0. This is the 0 of g of s, right? Negative 1. This is g of s is here. Negative 1. Negative 1 is the zeros of this g. And it is also the poles of t of s when k tend to infinity. Tk tend to infinity. K tend to infinity. You see? Okay, so now we know in this Locus, in this graph, it contains the part of PZ map of G. PZ map of G. These two cross and this circle, it is just the PZ map, the poles and zeros map of G of S. G is the plant of the system, right? G of S. And these two curves, they are the whole Locus. They contain the PZ map of G as part of it. which part? Actually, the cross according to k equal to 0. K equal to 0. And the circle according to k equal to infinite. So you can think the cross is the start and the circle are the end of the rule Locus. So we combine 1 and 2 together. We see rule Locus, root Locus start from a pole of g of s, and okay, this is a rule Locus starts from a pole of g of s and end at a 0 of g of s. So we have these. Alright. Then we will see the number of rule Locus equal to the order of g of s. Actually, this is the same with the order of t of s. They are same. These two orders, they have same order. The order contain both the numerator and denominator. If g has more roots, more poles, then how many poles, then how many rule Locus do you have? They will be same. And if they have more zeros, then you also have same thing. Things like this. Like I like this one. You have, for example, like 3 poles, 2 zeros. If the G has 3 poles and 2 zeros, then we have 3 rule Locus. If G of S has like 2 poles, like 4 zeros, then I have 2 poles and 4 zeros. There's still 4 rule Locus. Yeah, 2 start from the cross, and another 2 will start from infinite. Things like this. Alright, things look like this. But in MATLAB, they have a requirement. They always consider these. They do not use this way. In MATLAB, always assume the order of g of s in denominator. Okay, I write this way. Always assume number of poles larger than or equal to number of zeros. Yeah, always assume like that. If we reverse, like for example, if I use, this is a G, I use another H, which is 1 over G, then can I have the root Locus of H? Okay, this is root Locus of H. H, I have 2 poles, 2 zeros and 1 pole, right? This is H. But you see, the Locus is still considered it as 2 poles and 1 0. So this is MATLAB. MATLAB always work like this. If you have more order in the numerator, then it will reverse it. It will reverse it. So always consider this case. Alright. Yeah. So when you have a transfer function looks like this, you have more zeros and less poles. When you have these Locus, you will think these two cross, they are the zeros. Those cross are zeros, and the circles are the poles. Yeah, but the graph should be same, right? Just change your order. This one we start. If you think this is a start point at the cross, then this is start point, right? The direction looks like this. And if you think these zeros are the start point, then it will the circle is start point, then the direction will be reversed. But the graph looks the same. The curve looks the same. Direction is different. The curves are same. Okay. This is the okay. And these are the 1, 2, 3. Okay. Then to go to the fourth. Fourth, we have something go to infinite, right? We have something go to infinite. Some velocity will go to infinite. Then how to any property about those infinities? Then we have these. We can have some example to look at some example here. For this one, yeah, here we have one example, right? We have one path go to infinite. One path go to infinite. Right? Then this infinite, if we only have one branch go to infinite, it must go along the negative of the real part, real axis. I say this is the the direction of losses go to or from infinite. Actually, yeah, I only have one. I needed more so you can see the rules. I have G is this, right? I have two poles. Now if I add one more zero, then the order of the denominator now is 3. So I have 3 poles. 3 poles, 1 zeros. 3 poles, 1 zeros. Then I need 2 lossy go to infinite, right? I have 2 lossy go to infinite. Over here, 1 is up, 1 is down. I have 2 go to infinite. 2 go to infinite. And if I have 3, no, I add one more. The order of denominator changes. So I have 4. Right? The denominator the order is 4, so I have 4 poles. And looks like this. I have 4 poles. This cross. I have 4 poles, and one Locus will go to this circle, right? This red one. Start from this cross and end it at this circle. And I need 3 more circles, but I do not have, so they go to infinite. One is these. This is also blue. This is also blue. This is a kind of a light blue. Go to infinite. This also go to infinite. This also go to infinite. This is the whole plane is a S plane, so it is a second dimensional. This is a second dimensional space. So you go to infinite, you can have direction. Use different direction go to infinite, but all of them go to infinite. This one go to infinite. This go to infinite. This go to infinite. So we have 3 go to infinite. And if we have more, okay, I give more, 6, 8, 9, 10. So this is order 8 in the denominator. Now you can imagine we need 7 root losses go to infinity, right? You can have, where are those 7s? It's here. You see, I have 7 go to infinity. 7 go to infinity. Now we can have some regulation, some like rules about it, right? Because the looks, when they go too far away from the original point, that means that when k is turned to be large, this root lossy looks like almost equal to a straight line, and they separate the whole space equal likely, right? The direction is totally 360 degrees, right? The whole plane. And these curves, they separate that as several pieces. Now is I have 7, so 7 of it. Separate the 360 degree into 7 equal likely angles, right? 7 angles, they're equal angles. Okay, so this is the rule. The direction will separate separate the whole 360 degrees equal likely. Equal likely. Yeah, separate equal likely. So like this one, then we have 2 branch go to infinite. Here is 180 degree, and this is another 180 degree, half and half. This one we only have 1. Okay, 1, then that like this way, go to infinity. Okay, this go to infinity. This go to infinity. There will be 306 degree, and this one will up like this. And if we have, you look at here. If we have like this one, then we have 7. We will have 7 directions. Each will be 2 pi over 7. The angle should be 2 pi over 7. Okay. Yeah. So, the direction. All right. And not only the direction. You see, they are symmetrically. Okay, not just these go to infinity. They are symmetrically. All the part is symmetrically. All the part everywhere of these velocities are symmetrically. So this is another part, another feature, another property. Actually, if A plus BJ is a pole, then we know A minus BJ must be a pole. So we always if A plus BJ is a pole, then A minus BJ must be a pole. So since if we have a pole here, then here must be another pole. If you have pole here, then here must be a pole. If you have a root lossy like this one go to this way, then here should we go this way, symmetrically. Symmetrically. Alright, so root Locus, root lossy, all the root lossy should be symmetric. They are symmetric according to the real axis. Yeah, according to the real x-axis. So the symmetric, yeah, you have a plus some imaginary part, then minus that imaginary part will be also a pole, right? Look like this. And okay, we go, yeah, this one we need more. Not just the direction, actually not just the direction. When we say the velocity, oh, not this one. I say they have the direction, right? The direction, when the velocity go to infinite, we have the direction. Not only direction, actually we have another two feature. One feature is those velocity, they were, you know, finally they looks like a straight line. It looks like a straight line. And also, you see, all these straight line, it seems to start from the same point, right? Yeah, it is not looks like this way. For example, like one is here, the other one is here. No, all of them, you look at them, they seems like start from same point. Start from same point, right? Start from same point. So we have a point. Actually, there is a point. That point can be considered the start of all these losses go to infinite, and this losses, when the k is large enough, they are almost a straight line. Okay, so we call these asymptotes. 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 Asymptotes of velocity as the k go to infinite, or maybe go to, maybe it's another direction. I say when s go to infinite. Yeah, when s go to infinite. So when the velocity, when s go to infinite. Yeah, no matter the velocity start from some infinite to zero, or start from across to infinite, right? Two directions, but they will always go to infinite. There are some straight line. So okay, some straight line. And all these straight line, they start from a point, from one point. That point is it's a real number. Actually, it's a real number. I say this is center. Okay, c equal to c real plus j times c imaginary. The c imaginary part is 0. The c real, actually this is c is just a real number. The center will be it's a summation of some poles. The real part of poles, and the minus the real part of, I write this way, of the zeros. Both poles and zeros of G. And divided by the how many asymptotes, the number of the asymptotes. Actually, this one equal to the number of poles minus number of zeros, and take absolute value. Maybe zero, you have more zeros, maybe you have more poles, so the difference between these two, and take absolute value, right? We have this. This is this one, asymptotes, number of asymptotes. Okay, start from the center. You have 1 point start, and the direction actually we just discussed, right? Now I give a formula for the direction. It start from the first angle here. Totally is 2 pi over, okay, I use these, I give a notation, I say this is a k. Suppose we have, not k I used, this is a m, okay, this is m. Suppose we have m root lossy. So you need divided 2 pi by m, this is the angle, this is the angle. So you always start from half of it. So this is a pi over m. And then you have 2 pi over m, and so on, depending on how many root lockers do you have. And this point is that C, the center. It's like this. So the direction, they will be pi over m plus 2 pi over m times k, lowercase k. This lowercase k will equal to 0, 1 until m minus 1. Totally m directions, right? We have m directions, m angles. Yeah. All right. So this is we call they are asymptotes. They are straight line. They are directly straight line. And the losses will start like, for example, the real loss is here. From the cross, start from here, and we're close to these asymptotes when s is large. Okay? The limit is the same with these, but in the beginning they are not same. We're close to it. Then here maybe another one close to it, another one close to it, things like that. All right. Okay, this is asymptotes, and okay, then we consider sevens. We have more feature. We look at here our graph. All right, yeah. When you have a curve like this, this related with the root lossy, they go to they have some imaginary values, right? The roots, the image with the image part, the complex poles. And when the root lossy locate in the real axis, they are real. Let me large. Yeah, they according to the real poles. All right. So you see, we have one segment here, and the other side. Oh, okay. This example is not good. I change a different example. Let me change a different example. I want if I have several. Okay. Let me work like this. I use s equal to transfer function of s. I use this s, and g. Now I let g equal to transfer, not transfer. I use s. So numerator is s plus 1. I still use one zeros, and 0. Okay, and the poles have s plus 1 is a pole, and s plus 2 is a pole, and s minus 3 is a pole, and s plus 5 give another pole. So I have 4 poles, right? 4 poles, but all the poles are real number. pole -1, pole -2, pole 3, pole sorry, I want this is the minus negative. There's a positive 5, so I have 4 poles, right? 4 poles. Then what is the rule Locus? The Locus of G. Okay, it looks like this. We have 1, 2, 3, 4. We have 4. Oh, one of it cancel. Yeah, I have 2 plus 1. That make a change. It's not so good. I use this 1.4, right? Then they are different. And rule Locus of G should be similar thing. Yeah, similar thing. So we have 1, 2, 3, 4. We have 4 poles, and 1 zeros. So the thing is, we have 3 branches. They will go to 3 losses. They will go to infinite, right? Yeah, 3 will go to infinite. Then we have 3 directions, right? This go to infinite. This go to infinite, and this one, the red one, also go to infinite. Other than these, now we look at all the poles in the real axis. You will see we have one part, and then some dash point. That's no way, right? No rule lossy, and then rule lossy, then no rule lossy, then rule lossy, then no rule lossy. So okay, so this is it always happen. So in the real axis, when you have several different pieces of rule lossy, then they were not directly connected. They have to have some kind of a gap here, some gap here. Actually, these gaps related with the negative k. Okay, let me talk a little bit about negative k, because rule Locus, the function in MATLAB, they only consider k is also only considered positive k. I think I explained for rule Locus, or in MATLAB here, right? Always assume number of poles are more than number of zeros, and k larger than or equal to 0. They have two assumptions. Now we want negative k. How to do negative k? I explain something in MATLAB. For rule Locus with k smaller than 0, we can think like this: g over 1 plus kg. Now k is negative, right? It equal to g over 1 minus negative k, but I use positive k times negative g. I choose plus k0. This k smaller than 0, and this k0 equal to negative k. It is positive. Make sense? Yeah. So this is a negative value, right? I use negative k. This will be positive value, but I move negative to g. So you just consider negative g. So this one, negative g. You run this, you will have the rule Locus for negative case. Okay, so we can have these. Hold on. Then rule Locus negative g. Okay, now in the graph I will have both. I have both. Make it large in the middle. Okay. We have 4 poles and 1 zeros. Okay, we choose which. Okay, these two branch up and down, and this red go to negative infinity. They are for the positive case, right? And this one, this for negative k. This for negative k, and this is also for negative case. And in the straight line, in the real axis, you will see this part, they are for positive k, and then this part, it was dash point before I gave the negative case, right? Before we gave the Locus with negative k, this part is a dash point. Actually, they are according to negative value of k. And then this part will be the part with positive k, and then this part will be with negative k, and the positive k again, and the negative k. So the thing is like alternatively, right? The whole real axis, it will be separated as several pieces. Each piece, the k will be positive or negative, so alternatively. I will say 7. The ruler C on the real axis how to say? So I say rule locker, right? Rule locker C, I use RL rule lockers for k larger than equal to 0, and ruler C for k smaller than 0 when they located on real axis will occur alternately, how to write? Sorry, I forgot that letter. Alternatively. Okay, I just like this. Yeah. So one positive, k larger than 0, then k smaller than 0, then k larger than 0, then k smaller than 0, like this. Yeah. Alternatively. And the most right part must be positive. How to say? Yeah, most right part must be positive. Most right part, right piece, right segment. In the most right segment, k must be positive. Yeah. Yeah. If we have some ruler C located on a real axis, so it must look like this. Let me see. The most right one. Yeah, I'm not so sure. Okay, you check the textbook. I think the most right. Let me see the graph here. Oh, it's not always, depending on the g. Actually, here like a negative g. If we only consider negative g as g, the most right. Okay, I don't have this. Sorry. That depend. Okay, depend. You need to check. Yeah. We will. Oh, maybe we need more assumption. Yeah, we have these, but we need more assumptions. Okay, with more assumption. Yeah, I erase it, but you should have it. In the most right segment, K should be positive. It is right. It is correct with some more assumption. That assumption is about that G. G can be written as some part with zeros and the poles and the coefficient. The assumption looks like this. G of S equal to some A times S minus 0, 1, S minus 0, 2, S minus 0, like N, and S minus pole 1, S minus pole 2, S minus pole M, A, and A positive, like this. If we have these, then we can have this one. Yeah. But if this A is you can use A as a negative one for this A, then the things will be different. All right. Okay. So these are the rule C and the real part. Okay. Let's go back to the graph. What else can we have? I have two. This is a two of it. Now let me redraw it. I only consider one. This one. Okay, we look at here. Look at the graph here. All right. Here we have something important here. You see, this point is kind of a special point. This point kind is a special point. We call these as a break point. This is a break point. Okay. So the break point, what is the meaning of the break point? Here should be two poles, right? Two poles. So every rule lossy gives us one pole, and this is intersection of two lossy. So that means at this point, two poles, they are same. In other words, you have multiple poles, multiple roots, right? We call this a breakaway point. This is the 1, 2, 3, 4, 7, 8. Breakaway point. Break point. I would say T of S has multiple poles at this point. Sorry, yeah. Break point. TS has multiple poles at this point. TS equal to G over 1 plus KG, and multiple poles, that means, how to say, I will write this way. Suppose G of S equal to a numerator over denominator, then T of S now is denominator plus K numerator, and here's a numerator, right? Like this way. D of S plus K N of S. Okay, I give a name. Like this point, I say it's a breakaway point. It's B. S equal to B. Then this one will equal to S minus B squared times something else. Like this. Yeah, maybe higher, but at least here's a square. Here's a square here. Then the B is is a pole of T, but actually two poles, right? Two poles at same point. Maybe here's a 3. So if this part, this part contain any more S minus B, then the multiple should be 3 poles, or even 4 and 5 poles at the same point. So this is breakaway point. You have these. Now how to find it? How to find the exact value? Here we have a graph. Actually, this graph is obtained by a kind of numerical calculation. It's kind of approximate, right? Approximate. If you click on it, then it is approximate of approximate. Because when you click, you will have some error, right? You cannot exactly put it in the right way. Here should be like I click here, the pole is 405, gain is 606.51. Yeah, things like, can I move it? Find it, make it more accurate. I can anyway. Now is pose at 407. Yeah, I move a little bit. Yeah, I have this one. So this is breakaway point, right? The break point. So the system has 2 poles at the same point. But if you want to know the exact value of this one, you need to try to solve it. Solve it mathematically. Move it. Yeah, okay, just like this. Yeah. Now how to solve it? How to find this B? Okay, we consider this. I write this as CHS. This is a characteristic polynomial. The denominator, this is denominator of a transfer function, is also called characteristic polynomial or equation. So we want this B. You plug B in, it must be 0, right? You plug B here, S equal to B, then this is 0. And you take derivative. This is also 0. This is also 0. Why? CH of S, take derivative on the S, or equal to, I have 2 part, right? I give a name. I call these as P of S, right? Capital P of S. Then it will be, I have 2 factors times together. I take derivative. So it is 2 of S minus B. I take derivative for the first part and keep P of S. Plus, I keep these. No change, but P take derivative. Right? I have these. Then you plug B equal to 0, S equal to B, give us 0, right? S equal to B, you get 0. So we have these two formulas. Okay, now we can solve it, because here we have 2 unknowns. Right? 2 unknowns, K and S. K and B, and 2 equations. Right? So we can solve. So to find K and B, right? Now we can try. I just use this example. Can I use this example? Oh, this is too large. It's fine. We can do it use a numerical way. Can I? Let me see. This is this is too large. We go back to the simple one. Okay, I go back to this one. This is a 1, 2. I go back to this one. Okay, G is this one. Then Locus of this one. Do I have breakaway point? Yeah. This one we also have a breakaway point. Right? Break point. The break point is here. Break point is here. Yeah. Then okay, it's an example. g of s, it is s plus 1 over s squared plus 1. Okay. Then ts, the whole transfer function of the feedback system, is g over 1 plus kg, which is this one in the numerator and times s squared plus 1, so I have s plus 1, and 1 times s squared plus 1, and the k of s plus 1, right, equal to this. So t of s equal to, then the characteristic polynomial is this one. It is s squared plus 1 plus k times s plus 1. Yeah, I write this way, s squared plus ks plus 1 plus k. Then take derivative. Take derivative. This is 2s plus k, right? Okay, consider equation is equal to 0 and equal to 0. Then we have s squared plus k s plus 1 plus k equal to 0, and 2s plus k equal to 0. Alright, this will be easy to solve because we have this, right? This gives us like a k equal to negative 2s. So we plug in this in the first. I get s squared plus k, which is negative 2s, times s plus 1 plus k, which is negative 2s, equal to 0. Alright, so this is s squared minus 2s squared minus 2s plus 1 equal to 0. Okay, these two put together is a negative s squared minus 2s plus 1 equal to 0. I see, s squared plus 2s minus 1 equal to 0. Then what will be the solution? Am I good? Negative k is negative 2s, negative 2s, negative 2s. Okay, so I have s equal to 2 times a is 1, the negative b plus or minus b is 2, negative b plus or minus square root of b squared minus 4 times a times c. So it's negative 2 plus or minus square root of 8 over 2. It is I cancel this 2, is negative 1 plus or minus square root of, I put this inside, 2 inside the square root, there will be 4. 8 over 4 is 2. So it is negative 1 plus or minus 1.41. Yeah, 1.41. Yeah, 1.41. So if I do plus, there will be positive 41 or negative 2.41, right? So I have two values. But you check the graph, you know, should be this one, right? It's the negative side. The pole is we can see here is negative 2.42. Actually, it should be this one. The exact value should be negative 1 minus square root 2. This is exact value, right? And what is a k? K will be negative 2s. So this is a negative 2 times negative 1 minus square root 2, which is a 2 plus 2 square root of 2. And this is 1.41, then 2.82 plus 2. So this is a 4.82, things like that. Oh, there should be something else. Yeah. So here the answer is 4.83. Now maybe this number is better than my number here. Yeah, than my number here, right? Okay. So you can find the break point. This is break point. Got it? Yeah. Okay. This is one thing. And it's a break point, and we also have the case when we check the stability. We hope all the poles they are located in the negative side in the left side of the left half plane of the S-plane, right? Okay, this example is always positive. Then we can, let me give a different example. I use a G equal to, I put a 1 here. What will happen? Oh, it's not good. I want put a 10 here. Yeah, still like this. Can I have I put negative 1 here. Okay, this is the case. Look at here. You see these two poles, they are in the right side. They have positive real part. So that means the system G of S, right? These two cross according to the poles of G of S. So G of S itself is unstable. And we add a K, add feedback. When K is changing, the pole's location is also changing. When K increase from 0, increase, at this point, it's a marginal case. And when K even larger, the system will go to a stable, right? The poles, all the poles will be in the left side, left half plane. So this point will be important. This point will be important. This point give us the place where give us a value on K. I want exactly with poles with no imaginary part. Can I? Okay, almost. See, the pole is 0.0096. It should be 0. I want to find point is 0, but I can't. It's hard to move this just with a 0 in the real part, no real part. Then the pole will locate in the imaginary axis. That is a marginal case. And I want to find that K and that pole. So this is the point. Okay. So this is another thing I want to discuss. This is one A nice. The intersection of root lossy with imaginary excess. Yeah. Intersection of root lossy with the imaginary excess. Some curves like this. Yeah. Imaginary. It's at this point. On this point. K is what? S is what? I want to know these two values, right? Two values. Okay, so this place, that is the case. T of S equal to 1 plus Kg, and 1 plus Kg of S equal to 0, and S has 0 real part. Okay, we need to solve this. So that means S equal to J times some W for some W. Which W we want to find? No, so far I don't know. So I will solve to find this W. Okay, we just plug in. I can use this example to explain it. Example, I have G of S equal to, I use the example here, equal to S plus 1 over S squared minus S plus 10. Alright, G of S is this one. then T of S, I only check this. So 1 plus K G is S plus 1 over S squared minus S plus 10 equal to 0, and S is J omega. So you want to solve it, I can plug in, and this is a fraction, so I can rewrite this in a polynomial, right? I times these, times S squared minus S plus 10. I times these on both sides. This side I have S squared minus S plus 10 plus K times S plus 1. Another side is 0 times it, still 0. And S is J omega. S is J omega, so I have J squared, which is negative, right? Omega squared, minus J omega plus 10 plus K J omega plus 1 equal to 0. Okay, we have a equation looks like this. This is the equation with real part and imaginary part, right? It's a complex equation, so I rewrite it in terms real part and imaginary part. So we have real part is negative omega squared plus 10, right? I have these, and K times 1, right? K times 1. This is real part. And the imaginary part, I have negative omega, I have positive K omega, right? Okay, I'll have this. Now this is a complex number. Complex number equal to 0. I need both real part and imaginary part equal to 0. So these give us two equations, two real equations. Omega squared plus 10 plus K equal to 0. Negative omega plus K omega equal to 0. Okay, here I get it. This is omega. Omega is I divided omega, so it's negative 1 plus K equal to 0. So K is 1, right? K is 1. And then I have omega squared equal to 11, right? 10 plus is 11. So omega equal to square root of 11. Positive or negative, right? Positive or negative. Okay, now we have the K equal to 1 and the poles are positive or negative square root this omega times J. Yeah. Now we can look at the graph here. This point, so the gain should be 1. Yeah, here I select I can only have 0.98. Should be 1. The gain should be 1, right? K should be 1, and the pole will be square root of 11. What is square root of 11? Square root of 11, it is 3.3166. Right. This is a 3.316 J. Alright, and right is 7 like this. And here in the graph I have 3.31, right? 3.31, almost same. Yeah, so this is the marginal point, and here's another marginal point, right? Symmetrically, here's another marginal point. And if this is like a design problem, you want to choose the right K so that the feedback system is stable, you will choose K larger than 1. Like here's K is 4.27, here's a K is 784, the gain is a K, right? And even larger to here, K is 11, K is 18. You can also choose K from this branch. K will be, now is 11, yeah, something. K is here is 7.38. Yeah, you can choose K in this side, and then you can have the poles of the whole system, right? Okay, So this is the intersection of the ruler C with imaginary axis. Alright, that's all for today. See you Wednesday. Okay, see you next time. See you Wednesday. Bye bye.